In this problem, we're computing the integral of 3x over the square root of x squared plus 1 on the interval 0 to 2. In other words, it's a definite integral. And we're going to compute this one by using an explicit u-substitution, and we're going to transform the limits of integration to u space. So I think the most sensible u-substitution here is to let the interior of that square root equal u, and then we'll just figure out all the other consequences of that substitution and transform the whole integral. So we let u equal x squared plus 1. Then we need to transform the differentials here. So du is going to be 2x dx. And by the way, I can already tell this is a hopeful substitution because it's not that hard to build a 2x into this numerator by just manipulating the constants. So we'll get to that in a minute. But I also want to transform my limits of integration first. So when x is 0, that's the lower limit. I look at my substitution here, u is equal to x squared plus 1, and I sub in x equals 0, and I get u equals 1. And our upper limit is x equals 2. When I sub in x equals 2 here, I end up with u equals 5. So now we're ready to transform this integral, but I am going to show one more in-between step before we wrap up the transformation. I'm just going to point out here that the original limits of integration are x limits, and we'll go ahead and transform those to u limits in just a second. And I want to manipulate this numerator in order to make this 2x dx piece appear. Now we have the correct variable piece there, that's an x. And we remember that constant multiples can move in and out of the integral at will. So I'm going to change this numerator to 2x. And that might seem like cheating at first, but all I've done there is divide a 3 out of the numerator and then multiply it by 2. Well, I can compensate for that by multiplying by 3 and dividing by 2 out in front. And we can see if I distributed that 3 halves to the numerator, it would indeed produce the original 3. So I've just built my differential du there, and then I'll go ahead and simplify the denominator at this point to the square root of u. So we're looking at the integral in kind of this hybrid form right now, where I have u's and x's, but I've built my differential du, that's 2x dx, and now I'm ready to finish the transformation. So I end up with a 3 halves, and now we'll have the integral entirely in terms of u, so let's go ahead and transform the limits of integration. Remember, the lower limit transformed to 1 and the upper limit to 5. And then the 2x dx just gives me a du. I'll just go ahead and write that at the end. So the whole integral just boils down to 1 over square root u du. So we're going to write 1 over square root u as a power function. And I get 3 halves integral from 1 to 5, u to the negative 1/2 du. And now I use the power rule backwards to get the antiderivative here. So I add 1 to the exponent, giving me a u to the 1/2. And then I divide by 1/2, which is the same as multiplying by 2. Now we're going to evaluate this as u goes from 1 to 5. So plugging in the upper and lower limits, I end up with a 3 times the quantity 5 to the 1/2. That's just square root 5. It's probably nicer to write it that way. Minus 1 to the 1/2. That's the square root of 1, but that's just 1. So that's a fine way to write the final answer, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.